Hello everyone, specifically ELT 132 Digital Electronics. So this video I was going to discuss DeMorgans theorem. Now DeMorgans theorem is really pretty straightforward because you're learning gates, and this gives you a method to make an AND gate out of an OR gate, or an OR gate, or vice versa, right? I was going to say an OR gate out of an AND gate. But generally, here are the rules. Let's take an example here. We're going to take, oh wait a minute, I got to do this here, right? I got to select this puppy, come over here, I'm going to select something like that. So let's try it. So we have a gate. This is an AND gate. Boom, boom, right? Now, we are going to put an inverter at the end, okay? That's the inverter, as best as I can draw it there. And this is going to be it's a NAND gate, right? However, this could be written as an AND gate with an inverted output, right? Forgive my handwriting, but you understand it. Here's your gate, and you just inverted the output. So this is an AND gate with an inverted output. Let's just go over the truth table. Let's do this pretty straightforward, a very easy way. So we're going to write the AND here. And what is that? It's going to be 0, 0, 0, 1, 1, 0, 1, 1, right? Those are your inputs. You can call this input A, and you can call this input B. Here you have A, and here you have B, right? Now, if you have an AND gate like I wrote here, this is it for an AND gate, right? What is our output going to be? It's going to be 0, 0, 0, and this will be 1, right? Now, if you have a NAND gate, I'm just going to draw another line down here. Okay. That was for your AND. Now, if it's a NAND, N, A, N, D, what's that going to be? It's just going to be the opposite of these, isn't it? It's going to be 1, 1, 1, 0. All I did, since we have an inverted output, if it's a 0, the inverter will make this be a 1. If it's a 1, it's going to make it be a 0, or turn it into a 0. Got it? So there's your NAND output. Now, tell me something. Look at this gate. What happens if we change the gate from an AND to an OR? Get it? That's your OR. Now, let's invert the output. So here we had an inverted output, didn't we? Let's invert it. So in other words, it's not inverted anymore, right? Because two negatives make a positive, so you don't need this anymore, right? What happens if you invert the inputs? Those are two inverter bubbles, right? So let's do the same thing. Suppose this is A, and this is B, and let's write it. Let's just write, let's come over here. We're going to write AB, A, B. It's going to be what? 0, 0, 0, 1, 1, 0, 1, 1. And this we're going to call your OR. And we're going to say with inverted inputs. Okay? So now we have an OR gate, and we have inverted inputs. So if these are 0, 0. Actually, that's going to be 1, 1 coming in, isn't it? Because if this is 0, you're going through the inverter, it's going to be 1. This one going through an inverter is going to be 1. And an OR gate with 2 1s is going to be 1, isn't it? Well, either one of these cases is going to be a 1 because one of the inputs would be a 1. Now, if both of these are 1s, A and B are 1, and they're inverted, that's like a 0, 0 going into your OR gate, and a 0, 0 going into your OR gate is a what? It's a 0. Now tell me something. If you look at this column right here, and you look at this column right here, what do you observe? They're the same, right? This one is the same as this one, right? Put a little arrow there. So basically what happened is when you change the gate, they made an AND gate to an OR gate, or an OR gate to an AND gate, and you inverted the inputs and inverted the outputs from what they were, you get the same logic. That's DeMorgans theorem, okay? Let me just do this again for you so you can understand it. Maybe I'll give you a little bit better example. Now what do we do here? I think I have to just hit the delete key. There it goes. Nice and clean, huh? Well, first, I want to show this to you in our expression. We have a similar gate. This is your OR gate with inverted inputs. And there's the expression, right? Here's your truth table. We just did it for you on the other screen. But you notice 1, 1, 1, 0, right? Now, this is DeMorgans theorem. 2 gate symbols, one AND shaped and one OR shaped, that are equivalent according to Morgan's theorems. All right. Two theorems in Boolean algebra allow us to transform any gate from an AND shape to an OR gate and vice versa. They didn't talk about the inputs there, but I'm going to talk to you. So notice what happened. You change your gate from an AND to an OR, invert the output. So since this was inverted, you don't have to invert the output. And you got to invert the inputs. Since these were not inverted going in, these are inverted going in. And these are equivalent gates. And that's what this means right here. So, this basically discusses what is done in the textbook. What is the shape of the gate? Is it an AND gate or an OR gate? What is the active level at the gate inputs? Are they inverted or not inverted? And what is the active level of the gate outputs? Is it inverted or not inverted? Those are really the questions you have to ask yourself. So really, if you have a gate, the 3 things you have to do in order to convert it using DeMorgans theorem, right? I'm just going to write them out for you. 1, no, I got to do this again, right? 1, all right, you're going to do this. You're going to change the gate. Specifically, that means AND. If it's an AND gate, you're going to move it to an OR gate. Or if it's an OR gate, you're going to change it to an AND gate. Get it? That's the first thing. Second, you're going to invert the output. Right. So if your initial output from your gate, suppose you have a gate like this. It's an AND gate, right, with 2 inputs. Nothing's inverted, right? Just 2 inputs. If you're going to rewrite this, since this is not inverted, now your output's going to be inverted, right? Well, yeah, you know what, that's the output. And I'm going to use this same diagram here for the next one. Let's just move you down here. We'll come back here. And now we're going to say 3. I'm going to say invert the inputs. Here, none of the inputs are inverted, right? So you're going to invert the input. So let's just look. What do you think this is going to look like? Let's just follow the rules. Change the gate. Since this is an AND gate, it's a 2-input AND gate. We got to make a 2-input OR gate. Inputs have to stay the same, the number of inputs. So it's going to be an OR, right? So let's do an OR gate. That's the best I can do right there. What does it say next? Invert the outputs. Well, this one's not inverted, so I'm going to write a little inverter bubble here. Draw your output. There's your inverted output. Invert the inputs. Well, these are not inverted. I'm going to write a little inverter bubble here, a little inverter bubble here, and bingo. There's your equivalent gate. Let's try something else. I'm going to make something else a little bit. Let's make this one a little bit more challenging, okay? Let me delete that there. Let's draw this one. How about this one? Here's your AND gate. Inverted output. One of your inputs is inverted, and one of them is not. I'm going to call this an AND. I'm just looking at the shape of the gate when I say that, right? So what is this equal to? Well, what's your gate? It's an AND gate. There you go. You know it's going to be an OR gate. It can't be anything else. My OR gates really are terrible, aren't they? What's the next thing to do? Invert the output. Is this output inverted? Yes. So if we wrote another inverter bubble here right after that, it's 2 inverter bubbles in a row. So they cancel each other out. So we can just draw the output. That's terrible, but that's a regular output. You get that, right? Sorry about that. There you go. Now what about the inputs? Well, this input is inverted, isn't it? Let's label each input, by the way. Let's call that A. Let's call this one B, right? A is inverted, so now your A input is just going to go right in there, isn't it? Because remember, if you inverted it, you have 2 inverter bubbles right next to each other, and they just cancel each other out. What about B? Well, B is going to have to go through an inverter bubble because it was not inverted. And guess what? This is an OR gate. Those are equivalent. I hope this video has cleared up any confusion there might be about DeMorgans theorem, but basically DeMorgans theorem is used so you can, I'm sorry about that, we got to get rid of that, to have equivalent gates when you don't have one. If you're building a circuit and you need an AND gate and for some reason you don't have one, but you have an OR gate, what can you do? You can use this theorem and you can simply use an OR gate instead of the AND gate, or vice versa. Right? That's really the beauty in DeMorgans theorem. I hope this has been helpful, and thank you very much.